Hey everybody, Vade here. Today is just going to be kind of like an introductory lesson to a very special integration technique known as integration using trigonometric substitution. Now, this, I would say, is a very common sense kind of integration technique in terms of why it works. Not necessarily in terms of how you apply it, because that you often have to be clever with sometimes. But hopefully after this you may be able to recognize at least some types of instances where like you'd be able to apply it. Now the reason why I'm saying at least why it's like common sense to understand it is because we're going back to the roots of right triangle trigonometry, like day one of whenever you learn trigonometry, like sine of theta equals opposite over hypotenuse, cosine of theta equals adjacent over hypotenuse, tangent of theta equals opposite over adjacent, stuff like that, trig identities. We're gonna go back to all of it, okay? Because all the stuff that I'm gonna be saying should be relationships that you kind of understand like are true. Okay, so let me start off here by giving you guys an integral. So like an integral, let me say like square root of 1 minus x squared here. I'm coming up with this on the spot. So this is the integral of the square root of, or let me do x squared minus 1 actually. X squared minus 1 dx. Okay, so try all the methods you want. U sub, parts, whatever it is, it won't work on this. Okay, so what can we do to make it simpler for us, or actually possible to solve? Well, I'm kind of tired of x and x, like our independent variable being x. I'm really tired of it. What if I bring in the world of theta? What if I just randomly, let me just let tangent of theta equal to the square root of x squared minus 1. You're probably like, Vade, how's that? Like, why? First of all, why are you bringing trig into this? Trig sucks. Trig was hell for me. Trig made me hate my life. Or is that even allowed? Like, are you allowed to bring in theta? Like this, like, why specifically tangent of theta? Well, first of all, again, independent variable here is x, okay? The integrand, right? It's x, okay? I can set it equal to whatever the heck I want, okay? Now, of course, you got to be mindful of, is this going to help you with it or not? It's kind of like u sub, right? If I let u equal to this, or I don't know, x squared minus 1, is that really going to help us? Well, I mean, again, I'm bringing the world of u, I'm bringing the world of x into the world of u, right? So, like, is u going to help us? Same with this, right? Like, I could have just set theta equal to this, but no, I'm setting tangent of theta equal to this. Like, it doesn't matter, okay? Because the world of theta is, like, foreign to us. We don't know what the world of theta is, right? So we can just set it equal to that. Like, it's completely unrelated. And by this, I'm defining a relationship, okay? So this is the hardest relationship that you're really going to encounter in this entire video. And it really is because it's something you have to get used to, right? The world of theta and the world of x are completely different worlds. Okay, I'm just connecting them. Okay, because I want to get this integral into a trig integral. And you're probably like, again, like, hey, trig is hell, man. Why am I bringing trig into this? It's not going to make life better. Oh, trust me, it will. You will be able to integrate this completely fine once you get it into a trig form. Okay, so don't say trig. Trig is actually going to be our best friend here. Okay, so I'm letting tangent of theta equal to the square root of x squared minus 1. So we're going to use the same logic we use when we set, like, for example, if we set u equal to x squared minus 1, okay, since we're in the world of single variables here, I can just do du, right, equals to 2x dx. So let's apply that same logic here to the tangent of theta equals square root of x squared minus 1. Let's do that. So let's have secant squared of theta, d theta, equals to then, I'm going to skip a little forward in this here. Like, I know that the square root, like the derivative of the square root of x is just 1 over 2 square root of x. Like, it's stuff like that, like small things. You can do the whole power rule, but just get it into this form. Because when we go to the right triangle trig, like, for example, we set tangent of theta equal to the square root guy over here. we want our answer in a square root, not with like exponents that like with fractions and stuff. Just it'll make more sense. So just get this out of the way here. So I'm gonna do that thing with the chain rule. So this will be 1 over 2 square root of then our x squared minus 1 times 2x, and then this will be dx here. And then our 2's will cancel, and then we get secant squared of theta d theta equals to x over the square root of x squared minus 1 dx. So we're almost done here. We have the square, we set tangent of theta equal to the square root of x squared minus 1 here, so we can rewrite this as secant squared of theta d theta equals to x over tangent of theta dx. So we're probably like, okay, we got this trig here, we have this trig, we have x here. Okay, we want the dx isolated, kind of like with our u sub, right? But how do we get that x? So this is where we do right triangle trig, okay? So again, the relationships I have thus far should make sense knowing, you know, how we do u sub, okay? Like, we're applying that same logic here. And this is going to be even more foundational because now I'm going to bring in right triangle trig, okay? And you're probably like, well, how's that going to help us? Well, you're going to see. We're going to get that x in terms of something in trig, okay? So we have a theta here. So tangent of theta, we said, is the square root, right? I'm going to bring the good old laser pointer here. The tangent of theta here is this, we said, is the square root of x squared minus 1. Remember, this is all over 1, so then this is adjacent, or opposite over adjacent. So this will then be opposite to theta is the square root of x squared minus 1, and adjacent to theta is 1, right? Opposite over adjacent. Pythagorean theorem, you know, right triangle, right? Pythagorean theorem, this will give us what? Square root of, and then square root of x squared minus 1 squared is x squared minus 1, and then plus b squared, or, you know, ab, whatever, and then plus 1 squared, which is 1. So this will be the square root of x squared. This will be positive x, you know, Pythagorean theorem stuff. You know, absolute value of x. No, we're Pythagorean theorem, okay? We don't do plus or minus or stuff like that in Pythagorean theorem, okay? Think of it like that. So in this case, what do you notice here? We have x in the hypotenuse. X over 1 is what we want, right? What gives us x over 1? Hypotenuse over adjacent. Which trig function is hypotenuse over adjacent? Well, we know that adjacent over hypotenuse is cosine. Reciprocal of that, right? Right, adjacent over hypotenuse is 1 over x. Reciprocal is x over 1. Reciprocal of cosine is secant. So secant of theta equals x. So we can just rewrite this as secant squared of theta d theta equals to secant of theta over tangent of theta dx. So now we'll have here, if we want to isolate our dx, okay, so we'll have, did I do this right? Secant of theta times tangent of theta d theta equals dx. Right, think I did that correctly. Yeah, secant of theta times tangent of theta equal d theta equals dx. So now, rewriting this integral that we were given into trig, right, we'd get the integral of tangent of theta, right, because the square root of x squared minus 1, and then times our dx. Now, dx is the secant of theta times tangent of theta d theta. So this will then be times secant of theta times tangent of theta d theta. Okay, so we're now in trig, and you're like, Vade, you said trigs are best friend. Well, we got to do some work here. So hopefully with the, again, so far, right triangle trig, the d theta and the dx, this should all make sense based off of your prior knowledge This should really make sense using fundamentals. Again, hardest thing to kind of think about is why I set tangent of theta equal to this, and just realizing that these are completely separate worlds, so we can do whatever we want here. Like I could have set tangent of u equal to the square root of x squared minus 1. Same thing. So what I'm going to do here is I'm going to rewrite this as what? Like tangent squared of theta times secant of theta d theta here. Now, I think I'm going to like apply a trig identity here. Like, let's see what happens. Again, completely natural. I just made up this problem on the spot here. Let's see if I can do it. Hopefully, if I can find a way to do this. But I see here that, what's the relationship between tangent and secant in terms of, like, a very foundational trigonometric identity? If you said Pythagorean identity, 1 plus tangent squared root of theta equals secant squared root of theta, you would be absolutely correct. So, remember that, like, 1 plus tangent squared root of theta equals secant squared root of theta. I think we have to use this twice. I'm pretty sure we have to, because I think we can do parts after some of this. We'll get tangent squared root of theta equals secant squared root of theta minus 1. So we can rewrite this here as secant squared of theta minus 1 times secant of theta d theta. So then we can distribute here, and I think we'll get secant cubed of theta minus secant of theta d theta. We can automatically take out one. We can rewrite it as integral secant cubed of theta minus, and then the integral of secant of theta. I proved this for my understanding. I'm memorizing videos. And again, this should be d theta minus ln absolute value of secant of theta plus tangent of theta d theta. And we'll put plus c at the end here. So now this integral here, this is one that we need to kind of pay attention to. This may be a little tricky for you to kind of get on the spot here, but I think I can help you out here because I notice a pattern. So we can rewrite this, the integral, and maybe you see, maybe you don't, of secant of theta times secant squared of theta d theta. Okay, so now hopefully you realize this is IBP. Okay, now why is this IBP? Well, think about DI. Like, again, if you know tabular, this is also, like, we're not going to use tabular in this case. It's just too complicated for us, or not as explicitly. It's not as straightforward as like regular tabular. But hopefully you see here, like, derivative of this is straightforward, and integral of secant squared, guys, is tangent, right? Hopefully you notice that. So that's why IBP seems like the right option. Seems. I'm not sure if it works, but let's see. Let's see if it does. So I'm gonna let u here. Did we use u here? We didn't use u. I just want to be consistent. That's all. I'm gonna let u equal to secant of theta, and then dv equal to secant squared of theta d theta. Then du will equal to secant of theta tangent of theta d theta. And then v, again, integral of secant squared, tangent, so tangent of theta. So then the integral of secant cubed of theta, I'm going to keep it as cubed of theta d theta. This will then be uv, so secant of theta, tangent of theta. And if you're wondering, I'm using parts. udv equals uv minus integral of v du, ultraviolet voodoo. So uv minus the integral of v, so tangent of theta du. Now, would you look at that? Would you look at that? And I'm going to rewrite it. I'm just going to write it straight up. Tangent of theta times secant of theta, tangent of theta. Tangent squared of theta times secant of theta. Isn't that something we were, like, just trying to do right here? This is like a cycling IBP right here. Okay, so we can actually treat this like a variable, but we have to wait here. I'm going to try, we can get this into a secant cubed of theta form here, and then we can solve for the integral of secant cubed of theta d theta that way. Now, if you're kind of confused by what I'm saying here, just wait. So let's apply our trig identity again. Let's just skip to the work that we got here. We got to this guy right here. This is something that we established here. I'm gonna put it in place of here. The reason why, again, this is our integral here. This is the integral that we had before. And again, we're trying to solve this here. This integral is equivalent to this is equivalent to this as seen by the equal signs. And we're trying to find this again. So I'm just going to put it with this here, and then you're going to see why that will work. It's a cycling IBP, but if you don't really know what that is, you'll see and you'll be like, oh my god, that's so clever. So secant cubed of theta d theta equals to secant of theta tangent. And again, what I may be doing may seem inefficient, so I apologize. If you have a better way of doing this, let me know in the comments. This is just what came to me in my head. So this will be minus integral of secant cubed of theta d theta minus ln abs value secant of theta plus tangent of theta. Okay. And so now what we can do here is we can rewrite it as the integral of secant cubed of theta d theta equals secant of theta tangent of theta minus tangent of theta minus the integral of secant cubed of theta d theta plus ln abs value secant of theta plus tangent of theta. Okay. Right. So now we can move this to the other side, and we can rewrite it as 2 times the integral of secant cubed of theta d theta equals to secant of theta tangent of theta plus ln abs value secant of theta plus tangent of theta. So now, to isolate this, we just divide by 2 on both sides. Right? You're probably like, wow, that's mind-blowing. And if you already knew this, then good for you. This will be integral of secant cubed of theta d theta. This will just be secant of theta tangent of theta plus ln abs value secant theta plus tangent of theta over 2. So now let's go back to this. This is what we were trying to find here. Okay, this is what we're trying to find. Again, we're going back to this guy right here. So we found this integral, and now we're just going to do that minus this ln here. So we can conclude this by saying, well, we can do integral of tangent of integral of whatever we had here, tangent of theta times secant theta tangent theta d theta. I don't know, tangent of theta times secant theta tangent of theta d theta equals to this guy right here, the secant cubed of theta. Again, I'm following this integral secant cubed of theta d theta. We found it, and that's where we plug it in here, and then do minus this ln right here. So this will then be the secant. I'm gonna just do 1/2 times secant of theta tangent of theta plus ln absolute secant of theta plus tangent of theta, and then minus this ln here, minus ln absolute value of secant of theta plus tangent of theta. Okay, and then plus, we can do a plus c here. Okay, so we're not done yet, okay, because we need to now put stuff in terms of x. We didn't start with trig, we started with x. So now we need to go back into the world of x because we started with x. So we have to now go back from the world of theta to the world of x. So now this is where our triangle helps. So we see here, right, secant of theta, and again, first of all, our answer is in terms of secant of theta and tangent of theta. Let's recall, using our right triangle here, that secant of theta is x over 1, right? secant of theta, and I'm just going to write x, right? Secant of theta is x, y, hypotenuse over adjacent, right? So x over 1, which is x. Tangent of theta, which we assigned right at the beginning, is the square root of x squared minus 1. So tangent of theta equals the square root of x squared minus 1, right? The square root of x squared minus 1. So now we can actually substitute this back in here. So we can say the integral of, again, if we want to do this entire thing, that's just going to be equal to our original square root of x squared minus 1. So the square root of x squared minus 1 dx equals to 1/2, and then secant of theta, which is x, then tangent of theta, which is square root of x squared minus 1, plus then ln absolute value of secant of theta, which is x, plus tangent of theta, which is the square root of x squared minus 1, and then minus ln absolute secant of theta x plus tangent of theta square root of x squared minus 1 plus c. If you want to take the derivative of this and see if it yields the integrand, be my guest. Again, hopefully I didn't make any mistakes. Please comment if I did. But yeah, this should hopefully make sense. Not necessarily like how to apply it, because you kind of have to be clever with it, but more about like the relationships, like why this works. Okay, like we used identities here, and we use right triangle trig. Like that should all really make sense. This is the hardest maybe thing to grasp in this problem. Like maybe why is it possible for that to occur? And again, world of theta, world of x, completely unrelated. You can do whatever you want with the theta here. So I just said tangent because I want to get this into a trig form that was easy to integrate, and then we could plug back in at the end. Okay, and this is what it got us. It got us a completely, like, if like we had an answer that had no trig in it because we were given something with no trig, and now we have an answer with no trig. So really cool manipulation technique. This is like, again, exploration. Hopefully realize like this is like a kind of form you maybe want to know. Hopefully you now like realize like integration, right? If I took the derivative of this, it would like of the square root of x squared minus 1, probably take me like 5 seconds. Integral of that, yeah, this took a while. Okay, so yeah, hopefully this was a good way to get you kind of into that territory of techniques to integration. Yeah, see you guys in the next one. I'll try to do more of these exploring lessons.